Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar, Haryana. Today we will be discussing about the module Pauli Exclusion Principle from the paper Atomic, Molecular and Laser Spectroscopy. You will be able to learn about the quantum states of electrons, Pauli Exclusion Principle, role in different fields, particularly the building block for atomic spectra. You will be able to learn about the quantum states of electrons, Pauli Exclusion Principle, role in different fields, particularly the building block for atomic spectra. Pauli Exclusion Principle. This principle is the quantum mechanical principle that states that two or more identical fermions, particles with half integer spin, cannot occupy the same quantum state within a quantum system simultaneously. In case of electrons in atoms, this statement can be read as: it is impossible for two electrons of a Pauli electron atom to have the same values of the four quantum numbers. The quantum numbers: n, known as the principal quantum number, L is the angular momentum quantum number, Ml is the magnetic quantum number, and Ms is the spin quantum number. If two electrons are lying in the same orbital and their n, L and Ml values are the same, then their Ms must be different. That infers the electrons must have opposite half integer spins of 1 by 2 and minus 1 by 2. This principle was formulated by Austrian physicist Wolfgang Pauli in 1925 for electrons and later extended to all fermions with his spin statistics theorem. However, particles with an integer spin like bosons do not obey Pauli exclusion principle because any number of identical bosons can occupy the same quantum state. The Pauli exclusion principle dictates the behavior of all fermions like quarks, electrons and neutrinos, that is half integer spin having 1 by 2 for electrons, 3 by 2, 5 by 2, etc. While bosons, particles with integer spin, will follow other principles. It is noteworthy, atoms can have different overall spin that determines whether they are fermions or bosons. Now helium-3 has spin 1 by 2 and is therefore considered as fermions, while helium-4 that has 0 spin and is therefore a boson. The theory of quantum mechanics describes the fermions by antisymmetric states. In contrast, particles with integer spin, that is bosons, have symmetric wave functions. Unlike fermions, these share the same quantum states. Fermions take their name from the Fermi-Dirac statistical distribution, while bosons have taken from Bose-Einstein distribution. Pauli exclusion principle through quantum mechanics. Quantum mechanically, Pauli's exclusion principle dictates that the total eigenfunction of a system of several electrons must be antisymmetric with respect to exchange of the coordinates, means position and spin of two electrons. Considering a system of two non-interacting electrons, one with potential energy and the eigenfunction and the second with values, as the electrons are non-interacting, total potential energy of the system is written by the following. Now if it is assumed that the electron 1 is in spin quantum state alpha and 2 in spin quantum state beta, total eigenfunction of the system is psi t is equal to psi a alpha 1 psi beta 2, and on exchange of the particles psi t prime is equal to psi beta 1 psi alpha 2. The total eigenfunction can be constructed by taking the linear combination. This satisfies time independent Schrodinger equation, and also the probability density doesn't change on exchange of the particles. constructing the symmetric wave functions and antisymmetric wave functions, which can be written as the symmetric wave function is equal to psi s is equal to 1 by root 2 psi alpha 1 psi beta 2 plus psi beta 1 psi alpha 2, while the antisymmetric wave function psi a is equal to 1 by root 2 psi alpha 1 psi beta 2 minus psi beta 1 psi alpha 2. Atoms and the Pauli principle. One of the important consequences of the principle is the elaboration of electron shell structure of atoms and the way atoms share electrons, thereby explaining the variety of chemical elements and their combinations. It is known that an electrically neutral atom contains bound electrons equal in number to the protons in the nucleus. Electrons are referred to fermions, cannot occupy the same quantum state as other electrons. So, electrons have different spins within an atom at the same electron orbital. Considering the case of neutral helium atom that has two bound electrons, both can occupy the lowest energy states by acquiring opposite spin. As spin is part of the quantum state of the electron, the two electrons are in different quantum states and do not violate the Pauli principle. As a spin can take only two different values, which we refer eigenvalues, and extending the concept to lithium atom with three bound electrons, the third electron cannot reside in 1s state and therefore must occupy one of the higher energy 2s states. The number of electrons in the outermost shell decides the chemical properties. The idea can be extended successfully to larger elements where shells of successfully higher energies are occupied. Solid state properties and the Pauli principle. In conductors and semiconductors, there are very large numbers of orbital that effectively form a continuous band structure of energy levels. In metal conductors, electrons lie in degenerate states that they cannot contribute much to the thermal capacity of a metal. Almost all types of mechanical, electrical, magnetic, optical and chemical properties of solids are the direct consequences of Pauli exclusion principle. Stability of matter with Pauli exclusion principle. The stability of the electrons in an atom is not directly related to the exclusion principle, but the quantum theory of the atom describes it very well. The Heisenberg uncertainty principle explains the idea that close approach of an electron to the nucleus of an atom necessarily increases its kinetic energy. The stability of large systems with many electrons and many nucleons is also explained by the Pauli exclusion principle. Freeman Dyson and Andrew Leonard in 1967 considered the balance of attractive, electron nuclear and repulsive such as electron-electron and nuclear-nuclear forces and showed that ordinary matter would collapse and occupy a much smaller volume without the Pauli principle. The Pauli exclusion principle suggests that the bulk matter is stable and occupies volume, as Paul Ehrenfest in 1931 has pointed out that the electrons of each atom cannot all fall into the lowest energy orbital and hence must occupy successively larger shells. Atoms cannot be squeezed too closely together and therefore occupy a volume. In conclusion, the electrons of the same spin are kept apart by a repulsive exchange interaction, that is a short range effect acting simultaneously with the long range electrostatic or Coulombic force. This effect is partly observed in the macroscopic world, that two solid objects cannot be in the same place at the same time. Talking about spin and the Pauli exclusion principle, the concept of spin was first discovered in 1922 by Otto Stern and Walter Gerlach, and they inferred from the famous Stern-Gerlach experiments that the intrinsic angular momentum or spin of a particle such as an electron is quantized which implies that it could only take certain discrete values. The spin of composite particles like protons, neutrons and atomic nuclei is the sum of the spins and orbital angular momentum of the constituent particles and is therefore follow the same quantization conditions. Spin is therefore a completely quantum mechanical property of a particle. There is a difference between bosons and fermions. Bosons have symmetric wave functions while fermions have antisymmetric wave functions. Just to understand the concept of spin, with half integer spin, that an electron has to spin around twice before it presents the same phase as earlier, while the probability waves of bosons flip or invert before they interfere with each other. Fermions, however, do not flip their probability waves. Therefore, the spins of particles need to be added together using special rules for addition of angular momentum. Another way of stating the principle is that no two fermions in a quantum system can have the same values of all four quantum numbers at any given time. A very high density white dwarf stars is explained, and also the very existence of different types of atoms in the universe and the large scale stability and bulk of matter. By recognizing the Pauli Exclusion Principle that no two electrons can occupy the same quantum state simultaneously, it effectively stops electrons from piling up on top of each other. This explains why matter occupies space exclusively for itself and does not allow other material objects to pass through it, and at the same time allows radiations to pass. The existence of the different atoms in the periodic table of elements and the sheer variety of the universe around us is also understood by this principle. In case an atom gains a new electron, it always goes into the lowest energy state available, of course, the outermost shell. Two atoms with closed shells cannot form a chemical bond with each other, as the electrons in one atom does not find available quantum states in the other that it can occupy. In this way, the arrangement of electrons in the outermost shell affects the chemical properties of an element and how atoms are able to bond and combine with other atoms. Same way, the molecules interact to form gases, liquids or solids, and how they aggregate themselves in living organisms. The Pauli Exclusion Principle explains the degenerate white dwarf, which is a type of star, as if two identical particles are forced to have the same quantum numbers, they respond with a repelling outward force known as degeneracy pressure or Pauli repulsion. The Pauli Exclusion Principle is one of the most important principles because of the three types of particles, which are electrons, protons and neutrons, from which ordinary matter is made up, which concludes that all material particles exhibit space occupying behavior. So let us summarize what we have learned about Pauli Exclusion Principle is that it is significantly important because it describes the quantum state of electron. This is a building block for development of the atomic spectrum. It is to understand that particles with integers known as bosons do not obey Pauli principle because any number of bosons can occupy the same quantum state, while Pauli has established that there cannot be more than one electron in the same quantum state. Thank you.